Let us study Gauss law now. For this, first let's take a big positive charge here. The positive charge is plus q, and then let's take an imaginary surface. Okay, this imaginary surface is actually a spherical surface. Okay, this is actually a spherical surface. It's in all dimensions. Okay, I'm not drawing the sphere properly. Okay, now it's correct. Now you see its radius of this will be small r, the radius of this sphere. This is an imaginary sphere. This imaginary sphere we say it as a Gaussian surface. Okay, this is the spherical Gaussian surface. Now let us see what will happen to the electric field. So this is a positive charge. So electric field will go outwards like this way. This will be the electric field. And then let's take a small area here. So this is a small area, and then from the small area we'll have an area normal. Okay, the area normal will be like this way. So the small area we say dA, and this is a small area normal, that is dA vector. You can see the electric field and the area normal are in the same direction. Okay, now let us see what is the formula for electric flux. Okay, electric flux formula is phi E is equal to, here in this case, closed integral of E vector dot dA vector. Okay, now you see we now have the formula A vector dot B vector is equal to AB cos theta. So let me use this formula here. So we have here EDA cos theta will come. Let me write that down. So we have here closed integral of EDA cos theta. I use this formula here. Okay, now let's see this thing. If you notice that the dA vector, this is the dA, the area vector from the picture you can see, and then the electric field both go in the same direction. So the angle between them is 0 degrees. Okay, so in this case theta is equal to 0. So what will happen to cos 0? Cos 0 is equal to 1. So in this case, instead of theta we write a cos 0 becomes 1. So we have here closed integral of E dA, and cos 0 is 1. Okay, so this will be the electric flux here. Let us take this equation number 1. Now let us see what will happen to the electric field. Okay, this is now see here the electric field is in all directions, so it is constant here. Okay, so it's also uniform, so we can take the electric field outside. Let me write down the electric field is uniform on the surface. On the surface of the sphere. Uniform means what? It's a constant. Okay, so we can say it is constant. So because electric field is constant, we can take out in the integral. So what we have now is E into closed integral of dA. Let's take this as equation number 2. Left side will have here electric flux. Okay, now we must find what is this area here. Okay, so this is the electric flux, or electric flux here, this is the area. If you see, we have a spherical Gaussian surface. This is an imaginary surface only, but it's spherical. So what is the area of a sphere? It is 4 pi r square. So let me write that down. Now let us see area of a sphere. That will be the closed integral dA, this part, that will be equal to 4 pi r square. Okay, that's the formula. Then let us see what is the value for the electric field also. We derived earlier. Electric field formula is E is equal to 1 by 4 pi epsilon naught into Q by r square. Okay, let us substitute this in equation 2. So substitute in equation 2. So when you substitute, what happens? So when you substitute in equation 2, let us see, we have here electric flux phi E is equal to E, instead of E we have here 1 by 4 pi epsilon naught into Q by R square, then into this thing, closed integral of dA, that means 4 pi R square. So 4 pi R square. Now 4 pi cancels, R square and R square will cancel. So what we left with is this last one. So we are left with phi E is equal to Q by epsilon naught. Okay. So it's not so clear here, I'll write this side. So we are left with phi E is equal to Q by epsilon naught. This is called as Gauss law. This is a formula called as Gauss law. So what does it mean? It means that the total flux is equal to the total charge enclosed. So what is the charge in the surface divided by epsilon naught? Okay, epsilon naught is a constant. So this will give us the value for electric flux. This is a formula for Gauss law also, or the statement of Gauss law. Now we'll come to the statement a little later. Now let us see, if suppose we have a different surface, how to write. Now let us take a random surface, that is arbitrary surface. So for any arbitrary surface, that means any random surface. Okay, so let's see how a random surface looks. So again we have a positive charge here, plus Q, and the electric field lines go outwards like this way. Let me mark that. These are electric field lines. Now let's take random surfaces. For that I'll extend this also. So I'm extending it. Now let me take 3 surfaces. Okay, it's a random shapes. So let this be the first surface in any shape. So let this surface be A1. This area be A1. Now let me take second surface. So let the second surface be like this way. It's a random surface here. This surface is A2. Okay, so we can take I3 also. So but if you see, the net electric flux is constant, the same. So if you take any kind of surface, the electric flux means number of field lines per unit charge, that or Q by epsilon, the net electric flux will be same. So for any random surface, the net electric flux is the same through all surfaces. Same through all the surfaces. So we can take any kind of surfaces, A1, A2, A3, any number, the electric flux will be same. So let's write the Gauss law now. So we have the closed, or we have the electric flux is equal to the closed integral of E vector dot dA vector, the electric field dot the area vector, that's equal to Q by epsilon naught. Here this is Q enclosed. That means what is the charge enclosed by surface. Okay, we don't see what is the charge outside the surface. What is the charge inside the surface? These surfaces are Gaussian surfaces, these are imaginary surfaces. So this will be the final statement of Gauss law. Okay. So actually Gauss law means you must write this statement, phi is equal to Q by epsilon naught. Okay, you must take what is the charge enclosed by the surface.